All right, let's implement the learn algorithm together. I told you that the example was 1, 3, 8, 7, 4, 3. So we need to process the odd position numbers differently from even position number, right? So what we're going to do is implement the scheme is we're going to implement two functions. One for odd position numbers and the other for even position numbers. Okay. So let's define learn sum. So this is going to be a normal odd position numbers. So what we're going to do is, if n is smaller than 10, then we just return that number. All right. And what we are going to do when n is larger than or equal to 10, we are going to divide this number into two parts. So the last part, which is going to be n% 10, and all but last, which is n/10. And what we are going to do is return last plus, so here we are dividing 3 and the rest. And this rest is stored in this all but last variable, right? And we're going to pass this all but last to learn sum double. All right. And how do we define this learn sum double? So this one basically receives a number whose first number, so now this one goes to this learn sum double function, and the last digit was actually on the even position. So we need to double this number. All right. So what we are going to do is the same thing. Split this number into two parts. All right. And what we are going to do is we need to double this last digit, this one. However, if this one is larger than 9, for example, when it was 8, we need to double it, and it's going to be 16, and we need to add 1 and 6. And we know a special function for that, which is we implemented previously, this one. So we are going to call this sum digits function here. All right. And the next thing we need to do is, if this number is smaller than 10, then we just return this learn digit, right? However, if this number is larger than 10, for example, it has more than 1 digits like this, then we just removed 4 here, and all last here is going to be 1387. And for this one, we just need to do a normal learn sum. So what we're going to do is return learn digit plus, we're going to call the previous function, learn sum function, for this all but last. All right? So this is how we implement this learn algorithm. So when we call this lump sum function to our 138743, and it's going to return 30 as expected. So is there any question regarding implementation of this lump sum algorithm? So basically what we did was when we have two different behaviors, we are going to implement two functions and we're going to handle these two operations separately. That's the spirit of mutual recursion. All right, that was mutual recursion. And from now on, I'm going to talk about the differences between recursion and iteration. And you might say, what are the differences between recursion and iteration? You can do the same thing rather than doing recursion by iteration. So for example, we implemented recursion, we implemented factorial using recursive functions this way. So if n is smaller than 1, we just return 1. Otherwise, we're going to return n times factorial n minus 1. So this was how we implemented factorial, right? And we can implement this factorial function using iteration, the loop we learned. So in this case, what we're going to do is define two numbers, total and k. While k is smaller than n, we're going to increment k one by one. And we're going to multiply this k to total, right? So at first, k is 1, k total. K is 1, and total becomes 1 times 1. In the next iteration, k becomes 2. Then we multiply these 2 to k to total, and it's going to be 2. In the next iteration, k becomes 3, and we're going to multiply t times 3, which was 2 in the previous iteration. So it's going to be 6. So in this way, we can implement factorial using iteration. And in the end, we're going to return the total. So what are the differences between recursion and iteration? Mathematically, recursion is a relational equation like this. On the other hand, iteration can be expressed in this multiplication operation. All right? So mathematically, we can represent them differently. And another difference is we have two names for recursion. On the other hand, we have 4 names or 4 variables in the case of iteration. So we can do the same thing with smaller number of names when it comes to recursion. And we need to use more names in general for iteration. So is this the only difference? This might be somewhat confusing for some of you. However, when you learn computer systems or computer architectures, you might learn the difference between recursion and iteration. Recursion calls functions more than one time. So when you want to calculate factorial, let's say 5, it's going to call factorial quite a lot, like 5 times, around 5 times, right? However, when it comes to iteration, we just call this factorial function once. So recursion involves many function calls. And when you call many functions, they affect a memory called stack memory. You are going to learn the concept of stack memory in the computer systems or computer architecture classes. So sometimes this might be problematic. So in general, people recommend iteration. However, if the problem is quite simple and it does not involve many function calls, then people prefer recursion. So according to your application, you need to choose whether you are going to take the approach of recursion or iteration. All right. So that is another difference between recursion and iteration. If you can understand this concept, don't worry about it. When you go to computer systems and computer architecture classes, they will teach the same thing. And how can you convert recursion to iteration? Iteration is a special case of recursion. And can you convert the following recursive function into a iterative function? So I'll give you some minutes and try to convert this recursive function into an iterative function. Does anyone need more time to think about it? Okay, let's convert this function into a iterative one together. When you convert a recursive function into iteration, you need to figure out what state must be maintained by the iterative function. So the answer might be this one. We need to keep the state of the digit sum, right? And we need to do this job again and again while n is larger than 10. So basically, in this case, we cared about the base case. And this base case was when n was smaller than 10. However, in this iteration, this is the opposite, right? We do this when n is larger than 10. And we're going to do the same thing. Split the number like less than n. You could call this all but last, but because of space limit, I just called it n. So we're going to split these two numbers like this. And then to the digit sum, we're going to add this last. And after this loop, we're going to return this digit sum variable. All right. So this is how we can convert a recursion into an iteration. And in the opposite way, we can convert iteration into recursion. All right. And in the previous slide, I told you that iteration is a special case of recursion, and recursion is a special case of iteration. And the state of an iteration can be passed as an argument. So here, we're passing these two states into a function itself as arguments or parameters. All right. So when we are converting recursion into iteration, you need to think about what state you need to maintain. On the other hand, in the case of converting iteration into recursion, you need to think about what parameters or what states to pass as arguments or parameters. All right. So you need to think about those two things. And I'm going to talk about tree recursion. So most of you guys might know what Fibonacci numbers are. So Fibonacci numbers are very simple. So the first Fibonacci number is 0, and the second Fibonacci number is 1. And how we construct the next Fibonacci number from the previous two, it's going to be 1. Summing these two, the next Fibonacci number is going to be 2, 3, 5, 8, 13, 21, like this. So this is Fibonacci, these are Fibonacci numbers. And can you implement a function that returns Fibonacci number like this? And you can implement this function using recursion. All right. Think about it for, let's just implement this together. I guess we are running out of time. So we're going to implement this Fibonacci number returning function. So what are the base cases? Can you guys guess the base cases? So from these two statements, we can directly see that these two cases are base cases. So we're going to implement these two parts. So when n equals 0, we're going to return 0. If n equals 1, we're going to just return 1. Otherwise, so these two are base cases. Otherwise, what we are going to do is return Fibonacci number plus 3 and minus 2. This is very simple, right? It's going to return Fibonacci numbers correctly, like this. However, this one entails some problem. So let's see what the problem is. When n is small, this is quite fast. However, Let's see what happens. So we are trying to print out Fibonacci number 34. And it's taking longer and longer time, like more than 10 seconds. And when n is larger than 35, it's getting a lot slower, like more than 24 seconds. So it's taking quite a lot of time, right? So let's stop here. So one of the problems of this naive implementation of Fibonacci number is it takes too much time. So why is that? This is called, so our implementation becomes very slow when n is larger than 35. So when we see what happens when we call Fibonacci 40, it's going to call Fibonacci 39 and Fibonacci 38. And Fibonacci 39 will call Fibonacci 38 and Fibonacci 37. What's happening here? So Fibonacci 39, let's say Fibonacci 38 comes up here, here, here. And 37 appears here, here, here. And 36 here, 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 right? So we are doing the same computation again and again. Specifically, when we are computing Fibonacci number 40 or Fibonacci number 41 minus k, they are computed Fibonacci k times, meaning that so many redundant computations are there. So the lesson or takeaway from here is blindly applying recursion is not always appropriate. And as I told you in the previous slide, that this will cause stack memory overflow error. Stack memory will be full because you are calling too many functions. All right. And how can you resolve this redundancy in computation? Any suggestions? Can you guys guess how can you resolve this issue? Yeah, Hein, Hong은, and Seungjae gave some ideas. And storing some computed values might resolve this issue. Yeah, that is correct. Let's implement that functionality together. So rather than calling this function again and again, what we are going to do is store the computed results. Or we can turn this recursive function into iteration. So by converting this function into iteration, we can store the computed values. So let's say the Fibonacci numbers, the first one and the second one is 1 and 0 and 1. And for I in range 2 to n, what we are going to do is append the new number So what we are basically doing here is adding the last two numbers inside here. And that is going to be the new Fibonacci number. And we're going to return the last number like this. All right. So let's see what happens. So does everyone understand this implementation? So this -1 indicates that the last item, and this one indicates the second last item. And adding to these two numbers, the last item, the second last item, gives next Fibonacci number. All right. So when we run this code, this one is much faster. All right. So as I told you, according to your application, you need to think about what approach you are going to take, recursion or iteration. I'm going to give you another example of recursion. Some of you might have heard about Tower of Hanoi. This is what we are going to do. Basically, what we want to do is move these plates. Let's say this one is destination, and this one is spare, and this one is source. So we have 3 poles and a number of plates like this. Let's say n plates. And we want to move all the plates in the source pole to the destination pole. However, the rule is like this. You cannot put larger plate on smaller plate. You cannot do this. All right. And how many times you need to move plates? What is the minimum number of moving that you need to do to move all these plates, n plates, from source to destination following this rule? Larger plates cannot be on top of smaller plates. In fact, we can solve this problem quite easily using recursion. So what we can do is, so what we are going to implement is move disk 1 from A to C, move disk 2 from A to B. So we want to print out the sequence of actions we need to do. Okay, so this is what we want to implement. Then how do we divide this given big problem into smaller ones? So how would you divide this problem into smaller ones? So let's have a look at what we can do. We're going to divide this problem in this way. Let's say we have n plates or n disks. And what we want to do is we first move n-1 disks into spare pole. All right. So we are moving these n-1 disks, the top n-1 disks, to spare pole. And next, what we are going to do is move this nth disk to destination. And then we're going to move this n-1 disks to the destination. So this is how we divide this problem. And we are not going to think about how we can do this, but we will just let our function perform this on its own. So that's the beauty of recursion. So in fact, this is the implementation. So the base case is when we have just one disk, then what we are going to do is move this disk 1 from source to destination. That's all we need to do. So if we have just one disk, then the problem becomes very, very simple. We're just moving that disk from source to destination. What if we have more than one disk? And as I told you, we're going to first move the n-1 disks from source to spare. Here, this is the position of destination, but the destination of n-1 disks is the spare pole, all right? And then we're going to move, so the first line, this line, corresponds to the second picture here. We're moving n-1 disks to the source pole. So this source pole is destination of this n-1 disks, okay? And then we're going to move the largest disk from source to destination. So this corresponds to this picture. And lastly, what we need to do is move this n-1 disks from source to destination, right? That's what this last expression is doing. So we are moving the n-1 that is positioned as spare to destination. So this is how we solve Hanoi. All right. So when we use recursion, we can solve this problem quite easily. However, when we try to solve this problem with iteration, it becomes very, very complicated. So this is the right place to apply recursion rather than iteration. All right, this one is a coding problem. This one actually appeared in the coding interview of Facebook, MS, Amazon, and Airbnb. Let's say you're partitioning a staircase, 계단, and it consists of n steps to the top. And the maximum part you can take each time is m. Then in how many distinct ways can you partition this staircase? So for example, let's say we have 6 steps and the maximum step you can take is 4. Then what we can do is first take 2 steps and next you take 4 steps and it's going to be 6 steps. So this is one way of partitioning these staircases. And the next case is take 1 step, and 4 steps. And 3, 3, 6, 1, 2, 3, 6, like this. So in how many ways can you partition this staircase, taking the maximum step of m? Try to implement this function on your own. We are going to discuss this problem in the next class, all right?